Alright, hi guys. How you people doing? Okay, so first of all, let me welcome you all to the Unacademy JEE English. This is a brand new channel by Unacademy, India's largest online learning platform for IIT JEE. And on this channel, everything is being taught to you completely in English, so that no student is leaving behind and every student gets to understand physics properly. Okay, so the topic that we were covering was electrostatics, and right now the subtopic that we are covering is electrostatics of a conductor. Today we'll be talking about the charge distributions on conductors. In my last lecture, I covered the properties of conductors in external electric fields and in the absence of external electric fields also. Alright, so based on that, today we'll be talking about the charge distributions. So whenever you give a charge to a conductor, how does the charge distribute? Okay, this topic is very important as far as the IIT JEE exam is concerned, because a lot of questions in JEE Mains as well as advanced are asked from this. The reason being that there are so many possibilities and the distributions can be very complicated. So pay close attention and make sure you understand the logic behind everything. Okay. So before we move forward, let me introduce myself one more time. My name is Rohit Dixit. I study mechanical engineering from IIT Delhi. I have more than 7 years of teaching experience, wherein I have taught at some of the biggest names in the industry. I myself was JEE rank 447, and I've already coached many students to top ranks in IIT JEE. Next, moving forward, let me also tell you a bit about the Unacademy subscription. Now, this Unacademy subscription comes with benefits like live classes. You get to interact with your educators. You have live polls and leaderboards. Yes, you can. We will be talking mostly about. I hope you're familiar with the basic properties, Pawan. If you're familiar with the basic properties of conductors, then also you can attend this. Okay. So you have live polls and leaderboards, you have test series and analysis, and you have live doubt clearing sessions. So all these plus points give your JEE prep a big boost. So remember that. And on top of everything else, you have access to India's best educators with your Unacademy platform. So how do you get this subscription? And how do you get closer to your goal of IIT? Hi Samarjit, how are you? So very easy. Follow these simple steps. Install the Unacademy app. Once you have done that, go to the plus section. Good afternoon to you too. And select your goal as IIT JEE. Then click on that Get Subscription button. Now the pricing of these subscriptions have been kept very modest. So a 24-month subscription comes at about 1500 rupees a month, which is hardly 50 rupees a day. So if you look at the 12-month subscriptions and the 24-month subscriptions, they are very economical. They have been specially designed for you guys so that you don't have to pay much. And so you're getting very good quality education at a very affordable price. Okay. And this can be made more affordable if you use my code, which is RD Live. So if you like my lectures, if you would like to attend my entire courses for IIT JEE Prep, you can get your subscription using this code. Okay. Next, you can join us on the Telegram app using this link, and also on the Telegram app using this link, you can join the group that I've created. Okay, and you can find me also. My user ID is Rohit_Dixit. Okay. Now, tomorrow I'm taking another important session which might be very helpful for you guys. So it's a very small session. Probably it's going to be half an hour to 1 hour or less than 1 hour, definitely. So we'll talk about how to make the most of your online lectures there. Alright, so without any delay, let's just get started with today's lecture. I'm good Samarjit. Thank you for asking. Alright, so first thing, last time we had discussed about the distribution of charges in conductors without cavities. So what did we learn? We learned that all the charge that is given to a conductor will come on its outer surface. It will distribute itself such that sigma at any point would be inversely proportional to r, where r is the radius of curvature. And I showed you the proof of that also. That proof of that was that ensures that all the points on the surface are equipotential. Alright, and then we also discussed that this was valid only if the charge was free to distribute itself. That is, if no other external charges were present or if no other external field was present. Now we are taking a different case where Your conductors have certain cavities. Now what happens? Okay, so we had discussed if there was a cavity and no charge was placed inside it, then no charge appears in the cavity, or all the charge still comes up and appears on the outermost surface. All right. So what happens when you place a charge here? When you place a charge here, we I think also discussed this. I'm just going over this quickly. A net charge of which is equal and opposite to the charge present inside the cavity will appear on the inside surface of the cavity. Now this happens in accordance with the Gauss law. We talked about this, that the easiest way to prove this is that you take a Gaussian surface like this. This is my Gaussian surface, as you can see. So I have chosen this Gaussian surface such that this entire surface lies in the volume of the conductor. And I know in electrostatic conditions, there is no E here. Anywhere inside the volume, the E drops down to zero. So therefore, the net flux passing through this Gaussian surface will always be zero, which means the net charge enclosed has to be zero. So immediately I can conclude that if a plus Q charge is kept here, then the charge appearing here would be minus Q only. So that the total charge enclosed in my Gaussian surface becomes zero. Alright, so how does this charge distribute itself? So and also a charge ensuring conservation of charge will appear on the outer surface. So imagine in this case, if my conductor was initially neutral. Now since minus Q charge came here, where does this charge come from? This is the free electrons running inward. So these will leave a deficit of electrons somewhere. So an equal positive charge would be left somewhere. And that net charge can only appear on the outer surface. So your outer surface will get a plus Q charge, so that you realize that your conductor also will remain neutral. Because the presence of this charge cannot create a net charge inside a conductor. It can only redistribute the charges. So that is what will happen. That is how the charges will appear the moment a charge is placed in the cavity. Okay. Now the charge distribution of the inner surface will be determined by the position of the cavity. Alright, I think we had talked about this also the last time. I told you, suppose this is my conductor and this is my cavity. So if the charge was placed perfectly in the middle, suppose this one condition, then you see the electric lines that would be originating would be symmetrical. Alright, and all these electric lines have to terminate on the inner surface because they cannot enter the volume of the conductor. Okay, remember this. No electric field lines can ever enter the volume of the conductor. So in order to terminate these lines, you need negative charges because electric field lines originate from positive charge and terminate at negative charges. So since you see in this case, the electric field lines are reaching everywhere uniformly. So the negative charge appearing would distribute itself uniformly. Alright, while let's take another case. So I have a similar cavity here. But imagine here I am keeping the positive charge somewhere here near one of the edges. Then what happens? Let's see. The electric field that this guy is creating, you realize it will be denser at a point which is lying closer to this. And the density of these field lines would be lesser at these points which are farther from it. Now less number of field lines are getting terminated here and more number of field lines are getting terminated here. So that immediately tells me that the density of negative charge that gets induced would be higher here and would be lower here. Okay, I seem to have okay, let me redraw this. So anyways, all the points which are farther away from my point charge will have lesser number of electric fields reaching per unit area. That is why the charge density induced here would be smaller, and you will see that this density would be higher for points which are near the place charge. So the charge distribution will depend on the positioning of the external charge. Hello Jaya, how are you? Hello Amy. Thank you so much. No problem. I'm just glad I'm able to help students like you. Okay. So I hope everybody followed this. So let me know if you have any confusion about any point written on this slide. If every point written on this slide is clear, then tell me, I'll move forward. Otherwise, I'll take up that point and discuss it again. So please let me know quickly. Are all the points written on this slide absolutely clear to you guys? See, you need to follow all the logics. You need to be convinced about every kind of thing that I'm telling you. Because if you are, then trust me, you will be able to solve the problems without any issue. Alright. So please respond fast. If everything is clear, then I'll move on. So either you can write all clear in the chat or you can write your doubt in the chat. Clear, sir? A bit. So what seems to be the problem, Pawan? Tell me which point seems to be the problem. If you let me know, I will try and help you. Maybe go through all the points once again. And if a problem still remains, then let me know. I will go over that point. Otherwise, I'll move on to the next slide. Oh, I think you may have some confusion because you did not attend yesterday's day before yesterday's class, right? That may be the reason why you may be a little confused. Yeah. I understand that. So don't worry. You can go through the previous lecture and you should be fine. Okay. All right. So let's talk about some important points related to conductors. So the first thing that I want to tell you is that the electric field due to any charges present outside the conductor will never reach a point inside the cavity also, or for that matter any point inside the outer surface. Alright, so whenever you have, what do I mean by this? I've shown you this, that in electrostatic conditions all the fields inside a conductor has to be zero. So imagine if you have any randomly shaped conductor and if you had charges kept near it. So all the electric fields produced by these charges, let's assume that it's a positive charge. So any electric fields that are being created by this will get terminated on the surface. They can never enter this. And so on. So any electric field lines will terminate on the surface only. They can never enter the subject. Yes, that is what a cavity is. Cavity is a hole. It's a hole inside something. So if you have a hole here, if you have an empty space also here, these field lines can never reach here. This electric field will never be able to reach this point, this space inside, a hollow space inside a solid. Okay. Next, similarly, the electric field due to any point charge which is kept inside the cavity can also never reach any point outside the conductor. So, in a similar fashion, I told you that if I keep any positive charge here, then all the field lines of this will terminate here. Alright, and they can never reach any point beyond this surface. So all the field lines of any charge kept outside will terminate on the outer surface. All the field lines due to any charge kept inside the cavity will terminate on the surface of the cavity. So neither can the field lines of this guy reach inside, nor can the field lines of this guy reach outside. Okay. Hence, a conductor divides the space into electrically isolated regions. Now, I can say any electrical activity happening here. If I bring more charges or whatever I do outside, that will only modify the fields in this region. So, anything that I do outside the conductor, it will only have its effect outside the conductor, and inside you will see no effects of that. Okay. So I can add more charges, I can move this charge. Even if I start moving this charge, if I start adding charges at different locations, all this will modify fields outside the conductor, but inside you will feel absolutely no effect of this. In a similar manner, if you start moving this guy here and there, you will see the fields inside changing, you will see the charge distributions here changing, but no effect can ever be felt outside. So I can say what a conductor is doing is conductor is dividing the space into two electrically isolated regions. Okay, so this being your one region, the part inside the conductor is one region, and everything outside is the other region. So everything around this is the second region. So these regions do not feel any effect of any electrical activity happening in the other one. Okay, so this entire thing would be a separate second region. Okay, so the idea is that anything happening in the green region would never influence anything happening in the orange region. Of course, this green region will extend up to infinity. Okay, similarly, anything happening in the orange region can never influence anything that is happening in the green region. Okay, they can never interact directly. The charges present inside the cavity can never interact with charges present outside the conductor. So we can say that these are electrically isolated spaces. Anything here is electrically isolated from anything which is inside the cavity. Okay, so please remember, this guy or any charges present outside will be isolated from this guy. They can never interact with this guy, and vice versa. So this result is the basis of electrostatic shielding. Now, electrostatic shielding means that I am shielding something from all the electric phenomena in another region. All right. So you must know about this, that all your watches come with a metallic dial only, always, right? Why does that happen? That happens because if there is any electric phenomena that is happening in the atmosphere, so any electric fields that are getting created because of winds, maybe because of friction between air molecules themselves or air and water molecules present in the air. So if your all the watch components are inside a metal casing, then any electrical phenomena happening outside will not alter the working of this. Similarly, if you remember, in your junior classes, you were told that in case of lightnings, yeah, you can say something like that. If you remember in your junior classes, you were told that if you are in a car and there is lightning outside, then you must always stay in the car. Why is that? Most of your cars, not most, all your cars are made of metals. So they are metal surfaces, they have metal surfaces, alright. So when you're sitting inside the car, you are actually sitting inside a cavity of a conductor. That is what you can say. So even if there is lightning and all here, those charges or those electric phenomena can never harm you inside. So it is always safe to remain inside of your car, because the metal body of the car electrostatically shields you from all the electric phenomena happening outside your car. Okay, so that is what electrostatic shielding is. There is something called Faradays cage, in which you have a metallic cage, all right, and you place any sensitive instrument inside that if you want to isolate it from any electric phenomena happening outside. So the moment you make such a cage of metal, anything inside can be isolated from anything that is happening outside. That is called a Faraday's cage. Anyways, this is they don't ask you much about this in your JEE, but yeah, they can ask you conceptual questions about shielding. Alright, note that any charge inside the cavity will also have no contributions to potential at any point outside the cavity. So please remember that. So what is happening is that when you have a charge placed inside the cavity, some charge is getting induced here, right? So if this was a positive charge, some negative charge is getting induced here. Now this negative charge, what it is doing, it is one cancelling the electric field lines of this guy. So if you notice, for anywhere here, the electric field due to this charge would be exactly equal and opposite to the electric field due to all these induced charges. So remember, so here the electric field is due to Q inside, E due to Q inside would be equal to minus of E due to charges induced inside the cavity. Alright. So Q present inside the cavity, that the electric field of that at any point outside the cavity will get cancelled by the electric field of the induced charges in the cavity surface. So that is true not only for this point but for this point also. Everywhere these are not letting the electric field of the internal charge get away anywhere outside. So they are always cancelling the fields anywhere. Similarly, they also end up cancelling the potential. See, how can I say that? If you talk about it, how do you define the potential? The way you define potential is so plus Q here, minus Q here. Alright. So let me denote the positives with red and negatives with blue. Then you have plus Q here also. So I hope everybody follows this. We have already talked about this. If I keep plus Q inside the cavity, then you will have minus Q on the inner walls of the cavity and plus Q appearing on the outer surface. Now you realize that if you have one case this and another case where I have just given this guy a charge plus Q. An identical conductor, okay, these two may not appear identical, but I have meant to make them identical. So imagine an identical conductor, and this time I am giving it some charge plus Q. So some plus Q is being given to this. So you will see that also distribute exactly the same. Okay. As I told you, in these cases, the internal charge distribution will depend on the position of this charge inside the cavity. However, the outside charge would be free to distribute itself unless there is an external electric field. So assuming there is no external electric field, it will distribute itself in a certain manner. If you had an identical conductor, a conductor with an identical shape, and you gave this also Q charge, it would also distribute itself perfectly identically. Now you realize, because of these charge distributions are identical, the fields in the space of these two would also be identical. I hope you can figure that out. That the field created by this guy and the field created by this guy in the outer space would be exactly identical. Why? Both the charges are distributed in an identical manner. And the fields due to these guys are never reaching outside points. So the only fields at outside points are due to these charges. And since these charges are identical in both the cases, the fields would also be identical. Now, if the fields are identical, then the potential of any point would also be identical. So the potential here would be same as the potential at a corresponding point here. So this potential is being created only by this charge. So how is that? What happens to the potential which would have been created by the small plus Q charge inside? The potential due to the positive charge inside also gets cancelled by the negative charges induced here. So the charges induced on the inner walls of a cavity not only cancel out the electric fields of the charge inside everywhere outside the cavity itself, they also cancel out their potentials. So remember this. So the induced charges will not only cancel the electric field due to a charge present inside the cavity for all points lying outside the cavity, they will also cancel their potentials. Okay, if you remember that, then you can answer some very easy questions. So okay, so yeah, I shouldn't have shown you this. This is supposed to be the answer. So let's try and see, if you have a charge of plus Q which is lying slightly here, then how do the charges get induced? So a negative Q a negative Q gets induced here and a positive Q gets induced here. So negative Q, you can see, is denser in a region which is nearer to your plus Q, and it is rarer. The density is smaller in a region which is farther away from Q. However, this Q, you realize, gets distributed uniformly. Okay, so that is an example where you can see how the charges are getting distributed. If you place a positive Q charge inside and a conductor which is which was electrically neutral earlier on, then you will see minus Q will appear here, and this charge would have a density which is higher in this region, density lower in this region, and correspondingly a plus Q charge would appear on the outer surface, which would be distributed uniformly. Okay, so that is an example that you can see. Okay, one more easy thing. Now I can ask you tricky questions also if you followed everything. So what kind of tricky questions can I ask? Let's see. So here, okay, I just told you here negative charges are getting induced. And here positive charges are getting induced. Now, what happens if I asked you, you have to find, let's say you have to find, I give you a point here which is at a distance x. So, what happens if I ask you to find the potential due to these charges at a point P? What is the potential that the charges induced on the inner surface of the cavity at point P? Okay, so you have to find the potential due to the charges induced inside the inner walls of the cavity at the point P. Now, it is very simple. You don't know the charge distributions, alright, but you know one thing for sure, that the induced charges will be able to cancel the potential produced at this point due to this Q. So here, due to this Q, the potential I know would be V due to Q would be KQ over X. So I immediately know V due to induced charges of the cavity would be minus KQ over X. Okay. So unless you realize this or you know this, that these guys will cancel all the potentials also created by this guy, then you wouldn't have been able to solve this because you have no idea about how the charge is distributed. But if you know, then you can easily say. Okay, so remember these facts. You can answer questions like this with the help of this fact. Now let's take up some more examples. What happens if there were two cavities and initially the conductor was neutral? So inside the walls of this cavity, minus Q1 will appear. Inside this, since this was minus Q2, a plus Q2 will appear. Now what happens outside? If this was electrically neutral, so outside surface will get plus Q1 minus Q2 amount of charge. The reason why I didn't draw it, because I didn't know whether it will be positive or negative. Okay. So this charge would get distributed on the outer surface. Okay, so right. So here it is. Alright, I hope you guys are following this. So when I had two cavities, place two charges, then how they are distributing. Please let me know that you're following this, because we are going to do some questions now. Alright, so let's see. So a charge of plus 3 coulomb is placed in a hollow cavity inside a large chunk of metal which is electrically neutral. Find the total charge on the exterior surface of the metal. So tell me the answer for the first problem. What is the answer for this? This is an easy one. It's just to quickly check whether you guys are following me or not. So what will be the answer of this problem? You have 4 options in front of you. Alright, I'm waiting for some answers. Please read the question properly. So you have been asked that a charge of plus 3 microcoulombs is placed in a hollow cavity inside a large chunk of metal that was electrically neutral. If the total, find the total charge on the exterior surface of the metal. Is it A 0 microcoulomb? Is it B minus 3 microcoulomb? If it is C plus 3 microcoulomb, or D depends on the shape and position of the cavity or where the cavity is located. Alright guys, I'm waiting for an answer. Okay, I guess you guys have fallen off to sleep. So this is very simple, by the way. The answer is plus 3 coulomb. See, that is it. That is the answer. Okay. Doesn't matter where the cavity is, doesn't matter how big the cavity is, doesn't matter what the shape of the cavity is. If the cavity has a charge of plus 3 microcoulomb, the inner walls of the cavity will get a charge of minus 3 microcoulomb. And because the metal was electrically neutral, the outer surface will always get a charge of plus microcoulomb, plus 3 microcoulomb. Similarly, in the figure shown, an arbitrarily shaped charge conductor is shown to you and some charge has been given to you. You've been asked at which point the density of the charge would be the least. So consider these. We know sigma inversely proportional to R. So this guy has R equals infinity. So this guy will have 0 sigma. So B will have the least density. Similarly, out of these points, A would have the highest density. Why? Because R would be tending to 0 for A. So this will have the highest density. Okay. Alright, now let's see. This is a very common way where how questions are asked of you. Alright, so the first kind of commonly asked questions are a distribution of charges in spherical configurations. So let's go over this first. All the charge given to a single shell will appear on the outer surface. The potential on the surface at any point would be kq over r. In case plus q will be distributed, in this case plus q would be distributed uniformly. Why? Because r is same everywhere, so that is why you will notice that plus q gets distributed uniformly. This should be very simple to follow. Okay, so I'll just move ahead. What happens when there are two concentric cells? So there are two concentric shells and I have given some plus q charge to the inner sphere and I have given some plus q2 charge to the outer sphere. Then let's see how the charges will appear. So let's first focus on the innermost sphere. I have given it plus q charge. That plus q charge will always appear here and it will distribute itself uniformly also. So all the plus q appears here. Okay. Now once plus q appears here, the only option for this guy is to have a minus q on the inner walls so that nothing gets through this. Okay, all the field lines due to this have to get terminated here. So it turns out that this guy will get a minus q1 charge only on the inner walls of the outer shell. Now, outer shell was given a total charge of q2 and it had a minus q1 charge here. As a result, the outer charge would come out to be plus q1 plus q2. Alright, and this will also be distributed uniformly. Okay, I hope you guys followed this. That if my q1 was given to the inner sphere, it will get all the q1 on its outer surface. As a result, the outer shell will get minus q1 on its inner surface. And finally, to ensure charge conservation, because the total charge that the outer shell can have has to be plus q2, because that was the charge that I gave it. So the outer surface will have a net charge of plus q1 plus q2 now. Alright, the potential difference or potentials at different points is as follows. This is very simple. I'm just writing the potentials due to both and adding them up. So potential on the inner sphere would be like this and potential on the outer sphere would be like this. Now you will notice this one thing, that potential on the outer surface depends only on, please remember this, this depends only on the net charge on the outer surface. So please remember this very, very well. Alright. So the potential of the outer surface will depend only on the net charge on its outer surface. The inner charges do not matter. Why? Because the potential of this is getting cancelled by the potential of this. Okay, when was that, Noman? I don't know. I'm sorry. I may have not realized it. You can call me again, maybe tomorrow in the morning. I may have been busy somewhere, Noman. Alright. Similarly, if you notice about the potential difference between the two, you will see that what is that coming as KQ1 over A minus KQ1 over B. So you will realize that delta V is independent of the charge on the outer surface. So please note this. Okay, that the potential difference is independent of the charge on the outer surface. It depended only on the charges on the inner surfaces. Okay, so you must realize that potential differences are work done. Work done would depend on these electric fields. These electric fields do not care about what charges are present outside. They are only determined by the charges inside. Why? Because these electric fields are getting created by these guys, and they are isolated from the charge outside. So that is why the outside charge is not mattering while calculating the potential difference between the inner shell and the outer shell. Now, in case you have three concentric shells, then assuming this was given plus Q1, so there are three shells which are given charges of plus Q1, plus Q2 and plus Q3. Let's see how they appear. So the entire plus Q1 here will appear on the outer surface of this. Now as a result, a minus Q1 would appear on the inner surface of this. Okay, so please remember, if any charge appears here, then an equal and opposite charge has to appear here. That there is no other option. Now the middle one was supposed to have a total charge of Q2. It already got minus Q1 on its inner surface. So now it has to get a charge of Q1 plus Q2 on its outer surface so that its total charge remains Q2. Now again, as this guy gets a charge of plus Q1 plus Q2, this surface has to get a charge of minus Q1 minus Q2. There is no other option. And if this guy got a charge of minus Q1 minus Q2, the outer surface of the third has to get this charge so that the total charge on the outermost shell remains Q3. So I hope you're following the logic. You can extend this logic for any number of shells now. Okay. Similarly, you can write the potential differences also. You can write the potentials and the potential differences. Now you will also know, realize that just like the last case, the delta V between any two spheres is independent of the charges present outside those spheres. So the delta V between this and this would be independent of these charges and all this charge and this charge. These charges would not have mattered while calculating the delta V between these. Similarly, while calculating delta V between these, the charges here, this wouldn't have mattered, how much charges here. And for calculating the delta V between these also, this wouldn't have mattered. So any charges which are lying outside the region of two shells between which the delta V has been asked, those will not matter. Alright. So quick tip, for any configuration, always write the charge distribution starting from the innermost shell. So whenever you have been asked to write charge distributions on any spherical kind of configurations, always start writing the charges starting from the innermost shell. Take all the charge given to the innermost shell, get it to its outer surface, then place an equal and opposite charge on the side facing it, then follow charge conservation and keep on marking the charges appearing on different surfaces. Similarly, for writing the potential at any shell, consider only the charges outside. You will notice that for the inner one, you could have just written the charges which are outside of this. For this one, you can only write for charges due to here and charges here. All right, middle one, and so on. All right. For writing the potentials, the charges inside do not really matter. As I said, all the inside charges will cancel out each other's potentials. Okay. The potential due to this shell would be cancelled due to this charge for any point outside. That is why we don't need to write the potentials of these shells. Alright, so why don't we try an example? So here you've been told find the charge distribution as shown in the figure. Also find the potential difference between the innermost shell and the outermost shell. So in this case, you have three shells of ABC and you are giving a plus Q charge to shell B. So you're providing a plus Q charge to shell B. Now you have to find the potential difference between the innermost shell and the outermost shell. Alright, so why don't I solve this? So first of all, what is the net charge that was given to A? It was 0. So it will have 0 charge here. Since it has 0 charge here, the charge appearing here would also be 0. The charge appearing here is 0. The entire Q1 will appear here. So plus Q1 will appear. Q will appear here. As a result, minus Q will appear here. As a result, plus Q will appear here because the net charge on C also has to be 0. So that is what my charges coming up on different surfaces will look like. A will have, the outer surface of A will have 0 charge. The inner surface of B will have 0 charge. The outer surface of B will have plus Q charge. As a result, the inner surface of C will have minus Q charge. And the outer surface of C will have plus Q charge. Now you would ask, the potential difference between the outermost shell and the innermost shell. So what is the potential difference between these two? First of all, the potential difference between these two, so VA minus VB or VB minus VA is 0. Why? Because this entire region has no electric field. And what do I know about regions which don't have any electric fields? So regions that do not have any electric fields are equipotential regions. Alright, I hope you watched the previous videos. If you haven't, you can watch it and you will realize what I am saying. Alright, this region has no electric field. So any such region which has no electric field will be an equipotential region. So everything inside this region is at the same potential. Alright. So all I need to do is find the potential difference between B and C. And I can do that very easily. Let's see what is the potential at B. The potential at B would be due to this. Alright. So it will be KQ over KQ over 2R. Similarly, what is the potential at C? See, at C, the potential would be due to this only. Because inner guys will cancel their charges, their potentials. So the potential difference VC minus VA would be, this is also equal to VA. Minus KQ over 4R. That will be your answer for potential difference. Alright. Okay, Ankit. Good to see you again. Next, let's talk a bit about the earthing of conductors. So, what is earthing? So, earthing means you're connecting something to earth. This is the symbolic representation. If you have any conductor, imagine you have any conductor and you draw this. That means I have connected it to earth. How am I connecting it to earth? Very simple. I'm taking a conducting wire. Conducting wire's one end is touching this conductor, another end is going and touching earth. Okay, as simple as that. That is what the earthing is. Now, earth behaves as a conducting sphere. We treat earth as a conducting sphere. Why do we do that? Because there is the presence of huge amounts of metals inside it. So, because of all these metals present inside the earth, earth can be treated as a metal conductor. Okay. Now, its potential. Obviously, how do I calculate the potential of a sphere? So, I calculate that as kq over r. Q being the total charge and r being the radius. So, that is how I can calculate the potential of earth also. Now, practically, I know all the charge transfers are happening in the magnitude of order -6. So practically all the charges that exist or it get exchanged happen in microcoulombs or even smaller, nanocoulombs maybe. So even if Earth may have considered a net charge, it would be of a few microcoulombs only. And what is the radius of Earth? Radius of Earth is 6,400 kilometers, which is 6.4 million meters. So now when you substitute values in this equation, see what you get. What am I getting my V for Earth? V for Earth is K, which is 9 into 10 to the power 9, Q roughly 10 to the power -6, and this roughly 6.4 into 10 to the power 6. So you realize this would come out to be roughly of the order of 10 to the power -3. Alright, volts. So this already comes out to be very, very less. And practically, I need a reference point also for potential. So that is why we treat the potential of Earth as 0. And we can consider that the potential of Earth never changes also. Even when I earth these metals, you will see that charges start flowing from this to Earth or from Earth to this. So even any such charge transfers, even after any such charge transfer, the net charge on Earth would still be in microcoulombs, and owing to the large radius of Earth, the potential of Earth can always be considered to be 0. Please remember this. So as all practical charge transfers happening in this, the potential of Earth is considered to be 0 at all times. So Earth is considered as a metal conductor which has 0 potential at all times. As a result, any conductor conducted to Earth will exchange charges, and with it will acquire 0 potential. Okay. So this is one more thing that you need to know. What happens when I connect two conductors? So there is one conductor, there is another conductor, and if I connect them to a wire. Alright, and imagine if one was had higher potential than the other. Imagine VA was greater than VB. Now, if you remember the relation between electric field lines and potentials, whenever you move in the direction of electric field lines, your potentials decrease. So if this is at a higher potential than this, which means the electric field lines between them have to be in this direction. Now these electric field lines, what they will cause is, when you connect them with a wire, the wire will carry a current which will move charges from here to here. Now you realize the potential of any conductor, kq over r, is directly proportional to q. So if the charge on A reduces, the charge on B increases, what will happen? That this will start going down and this will start going up. There will eventually come a point when the final potential at A would become equal to the final potential at B. And at this time, this electric field will disappear and the current here will become 0. Alright. So, any two conductors, when kept in contact, remember, will start exchanging charges, and they will continue to do so till their potentials become equal. Okay, so whenever you connect any two conductors, doesn't matter what shape, what size, having the same charge, having no charge, doesn't matter. If they are at different potentials, then they will exchange charges among themselves. The charges would flow from higher potential body to the lower potential body till the time when their potentials become equal. So this always happens. So what happens when you connect a conductor to Earth? Earth always has a zero potential. So the conductor which is connected to Earth will exchange charges with Earth. It will either give charges or takes charges until unless its own potential becomes zero. So that is what I was saying, that the result is that any conductor connected to Earth will exchange charges with the Earth and acquire zero potential. Okay, yeah. So how do the charges get distributed when there is a single shell which has been earthed. So assume that a conductor is given initially a plus q charge and it takes some charge from x from the earth. What happens? All the plus q would have appeared here, and if the conductor is taking some x charge from earth, I'm assuming that the total charge on the outer surface would be q plus x. So firstly that. Second, I know that the potential after earthing of this conductor will become zero. So I use that condition, and what I realize is that x equals minus q. So we notice that all the charge flows to earth and it becomes neutral. So wherever you connect anything to earth, this entire charge would essentially flow down to the earth and it will become neutral. That is what happens. That is why you earth electrical appliances at homes. At homes, you realize your refrigerators, they have surfaces made up of metals. So what happens in a dry day, in a day where there is no moisture in the air, due to maybe some kind of air friction, some charges may get exchanged, or some charges may start appearing on your metal surfaces of the refrigerators. Alright, so refrigerator is some weirdly shaped conductor having some charge. But what will happen when you earth it? The moment you connect it to earth, all this charge will always flow into the earth, and there will be no charge accumulation on the refrigeration door. So when you touch it, you won't feel a shock. If your earthing has a fault, then this charge that got accumulated on the surface might give you a shock. There might be times where you touched the surface of the refrigerator and you felt a shock. That was if your earthing line was faulty. Okay. So similarly, you can analyze other cases also. What happens when you have two concentric shells and the outermost shell is earthed. Alright, so in this case, I've taken an example where the inner shell was given an initial charge Q1, the outer one was given an initial charge Q2, and we assume, so plus Q1 was given to the inner shell, so all its plus Q1 would come here. Now, as a result, minus Q1 has to come here. It doesn't matter if the outer one got earthed or not. This is a must. This is compulsory. So as a result, what happens is I know that Q1 plus Q2 comes outside, and also an additional X comes from outside. Now, when I check the conditions, I find that this also becomes negative of this, which means all this charge, this entire charge will flow to earth. So what you realize is that whenever you connect the outermost shell of any number of shells, you can have any number of shells like this. Whenever you connect the outermost shell to earth, the charge here on its surface will always become zero. Okay, so remember that. That's a quick tip. Know that the charge of the outermost surface becomes zero again. So quick tip for any number of concentric shells, if with the outermost shell earthed, make the charge on the outermost surface always zero. Alright, you don't even need to think about this. So let's try to find the charge distribution in the situation given. You have this, and let's say you were given plus Q1. Assume Q1, Q2 and Q3 were initially provided to the three spheres. Then plus Q would have come here, minus Q here, plus Q1 plus Q2 here, minus Q1 minus Q2 here, and 0 here. Okay. Now I don't even need to check the condition whether the outside potential is 0 or not. It will be 0, trust me. You can check it, it will be 0. So that is how the distribution of charges takes place. Alright. Next, let us consider the case of parallel plate configurations. So, what happens when you have two or more conducting plates which are kept parallel to each other and charges are given to them. So, in the first example, I'm considering that a charge of plus Q is given to the plate. Assume it distributes itself as shown. So, I'm assuming that this gets divided such that some plus Q appears here and capital Q minus Q appears here. Now, since the net E inside the conductor volume has to be 0, we will get that small q equals q by 2. Okay. So, thus the charge will distribute itself equally. So, when you have this and you give this a plus q charge, q by 2 would come here, q by 2 would come here. As simple as that. You could have also said this from symmetry. Obviously, there is no reason why one side should get more charge. These two sides are identical, so both the sides will get plus q by 2 charge each. Okay. Note that we have assumed the plate has negligible thickness compared to other dimensions. Thus, each face can be considered as an infinite sheet, and that is why you're not considering any charge appearing here, appearing either here or here. You do not consider any charges appearing here. The entire charge Q is getting distributed on the two sides only. So, for all calculation purposes, I will be treating this plate as infinite sheets. Okay, please remember that. Next, what happens when there are two parallel plates and they are giving charges of Q1 and Q2? Assume it distributes itself in some manner. So, I have assumed this distribution. I have assumed that this guy is getting Q1 here, Q2 here. From charge conservation, I can say that this guy gets this much and this guy gets this much. Alright. Now, since the net E inside the conductor volume has to be 0, we will realize that Q1 equals minus Q2. Alright. As charges on the facing sides are always equal and opposite, please remember this. This is a very important result. Alright, charges on the facing sides are always equal and opposite, always, no matter what. And as a result, equal charges will appear on both the outer surfaces. So that is also an important result. Alright, let's see how that is happening. There is a very simple proof of that. So what you do is, you imagine a Gaussian surface here. Imagine a Gaussian surface here. So, since I told you we are treating these fields, these sheets as infinite sheets, the electric field between them, I am assuming the direction to be like this. But it has to be perpendicular to both the sheets, right? It could be from the other way also. It could be the other way, like from the, instead of this, it could happen like this. But it doesn't matter. It would still be perpendicular to the sheets. Okay. So assuming that this is the electric field's direction, and assuming that the charge density here is plus sigma 1, and charge density here is plus sigma 2. For right now, I'm assuming. So my Gaussian surface has a cross-sectional area of A. Now, what is the total flux passing through my Gaussian surface? It will be 0. Why? The flux passing through this is 0. Why? This entire surface lies inside a conductor. Inside the conductor, E everywhere is 0. Similarly, the flux passing through this is 0. Similarly, this surface, the A vector points like this, the E vector points like this. Okay. So, since your A vector points like this, E vector points like this, the angle is 90. For this surface also, the same thing happens. The 90-degree angle between the A vector and the E vector causes the flux to be 0. So, flux through all these surfaces is 0, which means the charge enclosed is 0. So, I can say now that since phi is 0, Q enclosed must also be 0. And what is the Q enclosed? Q enclosed is sigma 1 times A plus sigma 2 times A. So this gets me a result that sigma 1, and this would be 0 by the way. Sigma 1 equals minus sigma 2. So if the charge densities are equal and opposite, so the charges appearing would also be equal and opposite. Which would mean if Q1 comes here, this would be equal to minus Q1. Okay. Now, because of this, you realize that the net charge contained in these two is 0. The net charge is 0. The net charge, whatever total charge I was giving to both the plates, has to appear here. And you can see that this will also be equal. I can prove that, but I'm not going to right now. You can check any book for that. There's a standard proof of that. Alright, if you're not convinced, then you can ask me later and I will show you the proof. Okay. The proof is very, very simple. It's just that take a point here. For the E to be 0, E due to this guy should be cancelled by E due to this guy, which will tell you that they have to have the same charge. Okay, that is the logic I told you. You can check out any book. This is a standard proof. Now, quick tip. Please remember this while figuring out the charge distributions on parallel plates. For any number of parallel plates, all the facing sides acquire equal and opposite charges. Second, both the outermost sides always acquire equal charges, and that charge is always half the total charge on all the plates. Okay, so remember this. So let's use that here. So I'm saying here I have 3 parallel plates. They have been given charges of Q1, Q2 and Q3, whose values have been given to you. So Q1 is this, Q2 is this, and Q3 is this. Let's see, what is the total charge? What is the total charge? Total charge would be plus 3 minus 2 plus 5 microcoulombs. So that is 6 microcoulomb. So that is always going to be my first step when I am deciding how much charge appears anywhere. So first I calculated the total charge. Now I know half of this has to appear here. So plus 3 microcoulomb appears here and half of it appears here. So plus 3 microcoulomb appears here. Now I can start from any of the end plates. So remember this is how we are going to do it. So let's start with this end plate. So this Q3 was supposed to be 5, out of which 3 has already come here. So how much will come on the other side? Plus 2 microcoulombs. If this gets a plus 2 microcoulomb charge, the facing side has to have a negative 2 microcoulomb charge. Alright. And let's see what the Q2 was. Q2 was minus 2 microcoulomb only. So if this was minus 2 microcoulomb and there is already minus 2 microcoulomb here, the charge here has to be 0. If this guy has a 0 charge, this guy can also have a 0 charge only. All the surfaces facing each other in case of conductors always have equal and opposite charges. And I will now see that Q1 was supposed to be 3, which is fine. That is automatically taken care of. 0 here plus 3 here. So yes, my charge distributions are sorted. These are the charges that appear on different surfaces. Okay. Next, parallel plates with earthing. Now this is an interesting thing. If any of the plates in a parallel plate setup is earth, then the outermost surfaces always acquire 0 charges. Please remember this. This happens in order to minimize the potential energy of the system. All the charges can be found by using the rules which were discussed earlier, except for one. Now the plate that has been connected with earth, you cannot apply conservation of charge for this. So please remember this. Otherwise, everything else still remains true. If this guy gets plus minus Q, this has to get plus Q. All the other rules remain the same. This guy gets 0 and this guy also gets 0. So that rules also remains the same. These two will always get equal charges. Alright. Other charges can be found by, what you do is you can start from conservation of charge for this plate. Alright. I told you earlier that you could have started with either this plate or this plate. That wouldn't have mattered. So in this case, you won't start from this plate. Why? Because conservation of charge cannot be applied for this plate. However, you can start with this plate, apply conservation of charge, get the charge here, and get the charge here, and then apply conservation of charge here, and you can get all the charges like this. Okay? Alright, so let's go through a checklist for problem solving. So this checklist says that if there is a spherical configuration, always start distributing the charges from the innermost shell. The surfaces facing each other always get equal and opposite charges. Use charge conservation to find the value of all the charges. Next, is there earthing? If there is earthing, then do not apply charge conservation for anything that has been earthed. Neither the shell nor the plate. Assume it takes some charge from earth and find that x using the fact that potential would become 0. That is for the shells. But for shells also, I told you if the outermost shell is connected to Earth, the charge on it is always becomes 0. Similarly, whenever any plate, it doesn't matter whether this plate was connected or this plate was connected or this plate was connected. You connect any of these plates to the Earth, the charges here will always be 0. Any one, doesn't matter which one. Okay, if you connect two also, then also, yeah, it remains the same. So in case of parallel plates, doesn't matter what plate you're connecting to Earth, outermost plates, outermost surfaces will always get 0 charges. Okay, all the facing plates will always get equal and opposite charges. Alright, and if the earthing has not been done, then the outermost 4 faces acquire half of the total charge each. Alright, so that is it from my side. This lecture was slightly short because I don't want to start capacitors today. We don't have much time today. I mean, just have 10-15 minutes. So I'll be taking up capacitors from next class onwards. That is on Saturday. So till then, you guys go and practice problems about this charge distributions of conductors. Go to your HC Verma. There is a chapter on conductors, I think, and there's a chapter on potential. So the problems of this are given in the chapter which is marked potential. Look at the problems towards the end. Those deal with charge distributions on conductors. Go through them. They can be really, really tricky. You can see the previous year JEE questions also. They have been asked. A lot of questions have been asked. They are also very tricky. So go home, solve some problems, and next class we'll start with capacitors. Okay. So before I leave, let me remind you that you can get your Unacademy subscriptions using following some very simple steps. You need to install the app. Then you go to the plus section, select your goal as IIT JEE and click on get subscription. Okay. Next, while getting your subscriptions, you can use my code RDLive. This code will give you an additional 10% off. Alright, thank you. Now, if you like this video, if you thought that you learned something new, then please press the like button and share it with as many people as you want. See, Unacademy is providing you free education and quality education for free. So we want most number of students to benefit from this. So don't be selfish. Share this free knowledge. Share this free content with as many people as possible. All right. Also press the bell icon to get notifications of all the schedules of all the lectures and sessions happening on the JEE English channel. All right. The notes of all the slides that were used in today's lecture will be available for download in PDF forms. You can check that later within a day or two. Maximum in 2 days, it should be available for download in the description box. Okay. You can also join us on the Telegram app using the link shown above. Okay. And you can find me on the Telegram app using with the help of this ID. Okay. Next, do remember to join me online tomorrow for this live session, which will really help you. That is my personal opinion, because a lot of you guys are confused about how to deal with online lectures, how to study from online lectures. You're so used to your offline lectures that I think this topic needs to have a discussion. Next, before I leave you, let me remind you one more time, my code is RDLive. Use this code to get your Unacademy subscriptions and get an additional 10% off. Okay. Yes, Ankit. Tomorrow at 6:30, there's a special session. It's a Friday special. Alright. Alright, guys. So take care and I'll see you tomorrow. Bye-bye.